Welcome back to the basics of digital audio signal processing and machine learning for audio using Python. We are now on the DSP theory number 2, which is related to the code example number 2. As we've seen before in code example number 2, there is nothing new. We just used a different way to load the WAV file, and we also plotted the WAV file, but in terms of the theory there was nothing new. We've been talking a lot about bit depth and about bits, 16 bits, 24 bits. So now I will go through a binary numbers revision. So if you are familiar with binary numbers, you can skip this part. Perhaps you want to stick a little bit, so when we talk about bitwise operations, or maybe it's something new for you, but if not, you can skip. This is for those that would like to have a revision about binary numbers and understand a bit more. So when we talk about 24 bits, what does it mean? 16 bits, what does it mean? So let's talk about binary numbers. So a binary number is a number expressed in the base 2 numeral system, or the binary numeral system. So a method of mathematical expressions which uses only two symbols, typically 0 and 1. And this is exactly what we use. We will use numbers that can only have 0 and 1. When we are in the decimal system, a base 10 numeral system, then we have numbers that goes from 0 to 9, symbols that represents numbers from 0 to 9. But in our case it's a binary number, so we only have 0 and 1, two symbols. Well, any number can be represented by a sequence of bits, so binary digits, which in turn may be represented by any mechanism capable of being in two mutually exclusive states. In our case we are going to use zeros and ones. So this is how we are going to represent our numbers, bits. So how do we count in binary? So counting in binary is similar to counting in any other numbering system. We begin with a single digit, counting proceeds through each symbol in increasing order. So here we have this table where we have the decimal number and we're counting. So it's from 0 to 9. When we get to 9, then we start again, but goes a 1 to this here, so we get 10. And then it goes again from 0 to 9, and then when we reach 9, we go carry 1, and then it will be a 2, so we will have 20 after 19, and so on and so forth. The same is with binary number, but we only have two symbols. So after a digit reaches 1 in binary, an increment resets it to 0, but also causes an increment of the next digit to the left. So as we see here, we have 0 and 1, then we have 0, and then there's another digit for a 1 here. Then we will count more, so there will be a 1 here. Then if we add one more, so there will be 0, 0, and goes another 1 here. So we're increasing these digits here, and it goes following this sequence. Now here is a small animation that is counting in binary from numbers 0 through 31. So the logic is very similar to decimal numbers, but in this case we don't go from 0 to 9. Then when we reach 9, then you go back to 0, but we have an extra digit. So in binary it goes 0, 1, then you go 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, then it goes another digit to the left, so 1, 0, 0, 0, and so on and so forth. So as any numeral systems, we can also do some binary arithmetic. So we can do addition, subtraction, multiplication, and division. Here we'll just
look at the addition, and we'll see that 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, and 1 plus 1 is equal to 0, but there is a carry of 1. So 1 plus 1 equals to 2, which is equals to 0 plus 1 times 2 to the power of 1. So there will be also subtraction, multiplication, division, but for us at the moment this will not be very useful, so I will not go into the details of multiplication and division or subtraction of binary numbers. Another important thing when we are dealing with binary numbers, especially if you go into embedded processors, embedded systems, processors, writing firmware, dealing with registers, and then sometimes you have a register and each position of this register means something. So for example, you need to set a certain bit to 1, and then this will configure your processor to do something. So there is this thing called bitwise operation. So in computer programming, a bitwise operation operates on a bit string, a bit array, or a binary number considered as a bit string at the level of its individual bits. It's a fast and simple action, basic to the higher level arithmetic operations and directly supported by a processor. So there are many logic operators that are normally used with bits. So you will find constantly not, and, an or, exclusive or shifting. So you have a bit string or a bit array, and then you can shift bits left, you can shift bits right, everything will have a meaning. You can, for example, circular shift, so if you shift and then the bit doesn't disappear, but it goes circular, so the last becomes the first if you shift from one side, or the first becomes the last if you shift for the other side. And there will be all these bit operations. So what we are going to do is, instead of looking at this theory here, we are going to do some examples and work with binary numbers. The first thing we're going to look at is converting integers to binary and vice versa using Python. So it exists a very convenient function, it's called bin, and it returns the binary representation of an integer. So if here we print bin 5, we will get here 101, and it's the same that we've seen before, that 5 is 101, which is here. So then if we print here, we can represent a binary number if we put this 0b and then it's 101, and when we print we get a 5 here. And we can also print, so we have here one number and we're adding to the other number, and the result here is a 9 in integers. But we can also look at what is this 111, what is the 010, and what is 9 in binary numbers. So this was a 7, this was a 2, so 7 plus 2, it's a 9, and a 9 is a 1001. So when we add here, we will have 1 plus 0 is a 1. Here we have 1 plus 1 is a 0, but it goes a carry. Then we will have 1 plus 0 is 0, but we have a carry, so it will be 1 plus 1, then it will be 0 but goes another carry, so we have 0 here, and then we had the other carry here, so then it will be 1001. So we see here that we have two bit numbers. They each have 3 bits,
but when we add them, then we will need 4 bits to represent this number, which is a 9. So talking about this, let's add one more code here. Before I mentioned that everything in Python is an object, including integers, and now we are going to see how many bits is necessary to represent a certain integer. So let's call our number, it's an A, and this number will be 32. So now if we press this A and dot, so this A is an object of type integer, but it has a lot of methods and attributes. So we can do here the bit length, and it's telling us that to represent the number 32 we will need 6 bits. So now if we do bin of 32, and we see that we have here 1, 2, 3, 4, 5, 6. So it's a 1 followed by zeros. So that means that if we have an integer and we want to know how many bits we need to represent, we can use this method called bit length, and then we will have here this number here saying how many bits we need. So we can also take a look at help. So number of bits necessary to represent the self in binary. Self here, in this case, means 32. So this can be very useful if you have certain number and you want to know how many bits it's necessary to represent this number. Another important thing is to think of bits as powers of 2. So we have here, if we use 8 bits, that means that we have 2 to the power of 8 different possible values. In this case, so I'm printing 2 to the power of 8, and we have 256. So that means that we have 256 different possible values. And when we print here all the 8 bits are 1, the maximum value we can represent is 255, because 0 is also a number, and it takes 1 value position. So from these 256 possible values we have, it goes from 0, which is counted as a possible value, until 255. So if we want to know the 256, we will see that we need 256. We need 9 bits to represent 256, not 8. With 8 we can represent until 255. Here we have just an addition that we've seen before, and here we have an OR, and an OR can also be used to set some bits. So let's start with a more simple example. So we have a number. This number will be 101, and we want to set the digit on the middle. So this 0 here, we want to set it to 1. So we can set it with an OR, and the result should be 111, and this is what we have here. So you can have this longer binary numbers, and if you want to set some position, so you can, for example, now you want to set this bit to 1 and also this bit to 1. So you have an OR. This is an OR operation that will do this OR
with this. So in Bitwise, an OR, just for a bit of theory, is a binary operation that takes two bit patterns of equal length and performs a logic inclusive OR operation on each pair of corresponding bits. The result in each position is 0 if both bits are 0, while otherwise the result is 1. So this is the same example that I did here. 1 or 1 is 1, 0 or 1 is 1, 1 or 0 is 1, and 0 or 0 is 0. So the bitwise OR may be used to set the 1 to the selected bits of the register as we described here. So the same what we did here. Another operator we have is the AND. So the AND takes two equal length binary representations and performs this logical AND operation in each pair. So if both bits in the compared position are 1, the bit in the resulting binary representation is 1. Otherwise, the result is 0. So when we have an AND, so 1 and 1 is 1, but 0 and 1 is 0, 1 and 0 is 0, and 0 and 0 is 0. So only when we have two ones, the result will be 1. And we can also use this to clear some bits. So suppose we have this. Let's do a more simple example like we did here before. So now we have this binary number here, 1 0 1, but we want to set these two bits here to 0, so the result should be 0 0 0. What we can do is to have an AND, and then we'll set here 0 and here 0. So this in the middle here, it will be also 0, but if it would be a 1, it would not change. So we are going to set these two bits here to 0. So the result is 0 0 0, so it reduces to 0. But if there would be a 1 here, now this one here, they will not be changed, but the other, so the result would be 0 1 0. So we are setting this here to 0 and this to 0. And here we have a more complex number, and we are setting, so this this here is set to 0. So the last two are set to 0. This is what we are doing here, and this is the result that we have here. Another possibility that we have, that we mentioned, is the shifting, bit shifting. So let's print this shift left and shift right. So we have this 0 1 0. If we shift it to the left, so this one goes here, and here if we shift to the right, this one goes to the left. Here's to the right and here's to the left. So this will be 0 0 1, and here will be 0 1 0. And this is what we have. 0 0 1 is the same as 1, and 1 0 0. So this bit here moved to here, and this moved here. And there is some explanation here about the shifting operation. So we have a left shift and we have a right shift, so you can read this if you're interested. But one thing that is really important is that a left arithmetic shift by n is equivalent to multiplying by 2 to the power of n, and the right shift operation is the same as a division by 2 to the power of n. So if we have a number, let's say it's 32, and we want to divide it by 4, that means that we can do a right shift operation of 2 bits. So let's do this. If we have 32 and we have a right shift operator of 2 bits, we have the result is 8. So 32 divided by 4 equals to 8, and 4 is 2 to the power of 2. On the other hand, if we want to multiply, we can do the left shift operation. So now we are going to multiply 4 by 2 to the power of 2. So 4 times 4 is 16. So this can be very useful sometimes when you want to multiply or divide in a processor. So what is very important to understand, that all these operations that are trivial to us when we're dealing with computers, when we're dealing with mathematics, addition, multiplication, division, square root, the power, it's very trivial for us. But if you're going to program it in a machine level, if you want to make circuits that do these operations, things get really complicated. And then you need to go to the basics of what it means to multiply, what it means to divide, even to generate a sine wave for a processor. Here we just would use a function called sine, and then we can have this, but what is happening inside the processor is something much more complex, that if you go into embedded systems programming, or I also have a course, it's called the Basics of Audio Programming in C, you will see that a lot of operations that we think is trivial, in fact, it takes a lot of effort to implement it in machine level. Well, let's go back here to our binary numbers. So we will see later. So we've been talking the bit depth of audio usually is 16 bits, but it also means that we will see later that we can have different ways how to represent negative and positive numbers. So in one case we can use 1 bit to be the sign. So then we will have, if we are using 16 bit, then we will have only 15 bit left for representative values. So in this case, if we have a -1, it would be 2 to the power of 15, and this would be minus 32,768. On the other hand, if we have a 1, they will go until 2 to the power of 15 minus 1, because we are using also a space for 0. So 0 also counts, and in this case we will have 32,767. And if you remember our code example, in our code example 2, the maximum, so this was a sine wave, so it should go from -1 to 1 when we imported with librosa that uses a floating point series representation. But here the maximum value was 32,767 and the minimum value was 32,768, which is equivalent to what we just found out here. So that means that possibly the representation, we are going to talk about this when we discuss the code into the details, but we could be using a 16-bit audio depth signed. That means that 1 bit is used to indicate the sign, the sign if it's plus or minus, and the other 15 they are used to represent a value. So this is why we have here 32,767 for positive and 32,768 for negative. So the last thing I want to mention here is, for example, if you have in decimal numbers and you have this number 12, so we can decompose this as this 1 times 10 to the power of 1. This is the position 0 and this is the position 1 plus 2 times 10 to the power of 0, and then we have this 12. So if we would have, for example, another number, so let's see, 3 times 10 to the power of 2, so that means that it's 312. So 0, this position here represents something at 10 to the power of 0. This position here is something times 10 to the power of 1. This position here is 3 times 10 to the power of 2, because here we are talking about units. This is so it's like 10, 20, 30, 40, and this is 100, 200, 300, 400, which is exactly this here, 100, tens, and zeros. And the same we have for binary numbers. So for example, if we have binary 5, so that means that we have here a 1 times 2 to the power of 2, so we're here, plus a 0 times 2 to the power of 1, plus a 1 times 2 to the power of 0. This is a 5. So now if we have a 7, so a 7 is a 1, 1, 1. So here we have 1, here we have 1, and here we have 1. So it's a 7. And if we have, let's see, 12, so it's 1, 1, 0, 0. So here will be a 0, here it will be a 0, here will be a 1, and we need to include one more, 1 times 2 to the power of 3, because 0, 1, 2, 3, and then we will have a 12. So we can decompose also in every numerical numeral system. If it's a base 10, we would replace there, instead of 2 to the power of something, it will be 10 to the power of something. But we have here binary numbers, so this is how we do it. So we've seen what is binary numbers. We understand that the number of bits indicates how many possible values we have. So if it's 16 bits, that means that we have 2 to the power of 16 possible values. So this would be, if we're using just positive numbers, so this would be from 0 until 65,535, because we have 65,536 possible values. 0 also counts, so it goes from 0 to 65,536. But if we want to use also negative numbers, so we can, for example, use 1 bit to determine the sign, if it's a plus or a minus. So we will be left with 15 bits, so then we will have 2 to the power of 15 bits, and we've seen already what it means here. We can do with shifting operations, we can achieve some multiplications and divisions as long as they're equivalent to 2 to the power of the number of bits that we shift. We have seen how to set a bit, how to clear a bit, how to convert from integers to bits and vice versa. So this was our short binary numbers revision, but now you already have a background on the binary numbers. So play around, try to do some operations, try to convert from integers to bits, to binary number, from binary number to integers, do some addition, set some bits, clear some bits, and of course, if there will come some new things, we will go back to this topic again and explain it. But for now, that's it, and I see you on the next tutorial, where we will start going in depth, line by line, step by step, of these code example here. Of course, now we've already seen imports, so from SciPy import. We will not talk about this. We will just look at this wave file read function. We will go into the strings, so we will understand all these three different ways that we're talking here. We will go into this array. We will also go into matplotlib pyplot, which is a library for plotting, then how we can plot, and so on and so forth. So I see you next time.